Hi everyone. So this is lecture number 12 of counting and we will learn dearrangement in this lecture. Very important concept. Very few times GATE has asked this in GATE Computer Science, but yeah, like this might come, and now since for GATE Data Science they have less syllabus, so I'm expecting more questions from probability statistics and in-depth questions from probability specifically, because probability is core to ML, right? So you can have deep questions from dearrangements as well. So yeah, we will learn every concept which might come. So yeah, dearrangement. What is dearrangement first? We know what is arrangement. Very easy, right? Arrangement is permutation. Like in how many ways can we arrange n people in a row? Shuffle them basically. It's as the name suggests, dearrangement is what? Not arrangement. Okay. So there should be some notation of what is not here, right? There is a beautiful notation. So let's say there are the standard problem is letter boxes. Okay. So generally in at your home, if you have a complex or let's say 10 floors, so there will be numbered, for your flat, for your particular home, you will have one letter box, right? And your flat number will be mentioned, let's say 1, 2, 3. Okay. Let's say there are 3 people living in a certain society, there are 3 homes, and you have 3 letter boxes, 1, 2 and 3. And now 3 letters come. You have 3 letters, one for each person. This is for house number 1, house number 2 and house number 3. So what is arrangement? What is so ideally what should happen? Like the letter number 1 should go in the box number 1. The letter number 2 should go in the box number 2, and letter number 3 should go in the box number 3. What is dearrangement is, in how many ways can I put these 3 objects in these 3 boxes such that no object goes in the correct position. That's why dearrangement, okay? Not an arrangement. What happens is, none of the object goes in at the correct place. Basically, 1 should not go in this 1. 2 should not go in box number 2. And 3 should not go in box number 3. Which means that you can have 2 here, 3 here and 1 here. This is okay. Right? Similarly, you can have 3 here, 1 here and 2 here. This is also okay. But let's say 2 here and 1 here and 3 here. This is not okay. Because the letter number 3 is in the correct box. This is not allowed. Similarly, 1, 2, 3 is also not allowed. Because all 3 are in the correct box. This is definitely not allowed, right? So this is the dearrangement. In how many ways can we put n objects in n places such that no object is in its correct place? Right? And see, this is tricky. You don't know. We don't have a way to calculate this yet. We know a way, and that is using inclusion-exclusion. Again, so in the last lecture I told you, when you don't know the answer to the no problem, see, no object can be going in the correct place. We don't know the answer to the no problem, but we know the answer to the yes problem. In how many ways can all 3 letters go in the correct place? 1 way. You put 1 here, 2 here and 3 here. In how many ways can letter 1 go in the correct place? There are 2 factorial ways, because 1 has to go here and 2 and 3 can go anywhere, right? We know the answer to the yes problem, but we don't know the answer to the no problem, right? So that's where we apply inclusion-exclusion. So we will solve this. So this is the question. 3 letters numbered 1, 2 and 3 have to be placed in 3 covers numbered 1, 2 and 3. In how many ways can this be done if no letter goes in the same numbered cover? Okay, same problem. And we are also assuming that no cover remains empty. Okay, this is all based on the assumption that no cover can remain empty. You have to place 1 letter in every cover. So we will use inclusion-exclusion to solve this. So we have 3 covers, 1, 2 and 3. And we have 3 letters, 1, 2 and 3. Okay, we have to place them here. So again, inclusion-exclusion, let's say set S1 is what? Letter 1 goes in cover 1. Letter 1 goes in cover 1. Similarly, S2 is letter 2 goes in 2. And set S3 is 3 goes in 3. Okay. Again, it's a symmetrical problem. So how many total arrangements are there? There are 3 factorial, which is 6 arrangements. There are 3 factorial total arrangements. and we will subtract S1, S2 and S3. Inclusion, exclusion, right? We don't want the letter 1 to go in cover 1. So we'll subtract all the ways in which letter 1 actually goes in cover 1. Again, we will subtract all the ways in which letter 2 actually goes in cover 2. And again, we will subtract letter 3 going in cover 3. But when we subtract this, we are actually undercounting. So when both 1 goes in 1 and 2 goes in 2, we are subtracting it twice. We have to subtract it only once. So we have to add it once. Inclusion, exclusion, right? Plus S12 plus S23 plus S31 minus S123. Okay, so what is this? This will become 3 factorial minus all these 3 will be same. This is a symmetrical problem. You like do any one of them, the answer will be same. So 3 times. Now letter 1 goes in cover 1. So in how many ways can we arrange the other 2? 2 factorial ways. Now plus 3 times. These 3 also will be symmetrical problems. So we can solve any one of them. Let's say 1 goes in cover 1 and also 2 goes in cover 2. Now if letter 1 is going in cover 1, letter 2 is going in cover 2, what happens to the third cover? There is only one letter left, right? You have to put it here. There is only one way to solve this. So 3 times 1 and minus all 3 of them are true, which means 1 goes in 1, 2 goes in 2 and 3 goes in 3. Again, there is one way to do this. 1. So it becomes 6 minus 3 times 2. 6 minus 3 times 2 is 6 plus 3 minus 1. So it becomes 2. Okay. There are only 2 ways actually, it seems. And we actually have written it here. Right. So there are only 6 ways, right? I can actually enumerate all the 6 ways in which we can arrange 3 letters. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2 and 3, 2, 1. And the cover number are 1, 2 and 3. So this is definitely not allowed. 1 is in 1. This is not allowed. This is also not allowed. Letter 1 is in cover 1. Is this allowed? 2, 1, 3. This is allowed. No letter is in the correct letter. Okay, so this is also not allowed. 3 is in the correct position. This is also not allowed, right? 3 is in the correct cover. 2, 3, 1. This is allowed. 3, 1, 2. This is also allowed. 3, 2, 1. This is not allowed because letter number 2 is in the correct cover. So there are only 2 ways, which we have written here as well, right? Cool. So the number of this is called the number of derangements of 3 letters, or basically the number of derangements of a set of size 3. The number of derangements of a set of size 3 is 2. There are only 2 ways in which we can dearrange 3 numbers, 3 words, whatever, right? So this is a standard combinatorial notation. We have a combinatorial notation for this as well. We know that the number of arrangements of n objects is factorial n. Then the number of derangements of n objects in a row is subfactorial n, denoted by this. We write the factorial symbol before. Okay, this is a standard notation. This is n factorial, this is subfactorial n, which means the number of derangements of n objects is subfactorial of n. So in combinatorial mathematics, a dearrangement is a permutation of the elements of a set such that no element appears in its original position. The number of dearrangements of a set of size n is known as the subfactorial of n, or the nth dearrangement number, or also the nth de Montmartre number. This, no one will ask you this, but for the sake of completeness, it is also called the nth de Montmartre number. Okay, it is denoted by dn, or the basically nth de factorial dearrangement number, or the subfactorial of n. Okay. So these are the notations. So now this is the formula. We will try to derive this formula. We already have derived it for 3. Okay. We have already derived it for 3 objects. We know that the answer is 2. Now we want to derive it for general n objects in n places, right? So let's say now we have four objects. So just to give you an idea, let's say we have 4 objects. Again, we will have 4 sets. This is like cover number 1, cover number 2, cover number 3, cover number 4, and we have 4 objects 1, 2, 3, 4. Set S1 is what? 1 goes in the correct cover. Set S2 is what? 2 goes in the correct cover. Set S3, 3 goes in the correct cover. And set S4, 4 goes in the correct cover. So permutation wise, like how we will solve this using inclusion exclusion, there are 4 factorial total ways. Minus S1 minus S2 minus S3 minus S4, all of them will be same. So 4 times the cardinality of any one of them. Plus again, now what will happen? S1 S2, we will have to add S1 S2, S2 S3, S3 S4. So basically this becomes 4 factorial minus 4C1, because we have to make any one condition true, one at a time. So 4C1 times cardinality of any one of them. Plus now we have to do 4C2 times, which means we are taking 2 at a time. S1 S2 are true, S1 S3 are true, S1 S4, S2 S3, S3 S4. So there are 6. So 4C2 times cardinality of 2 of them being true. Basically 1 goes in 1 and 2 goes in 2. So this is like cardinality of S12. You can write it S12 minus 4C3 times minus plus minus, inclusion exclusion, right? Now cardinality of 3 of them being true, and plus 4C4 times cardinality of all 4, right? So what it will be? 4 factorial minus 4C1 times, what is the cardinality of any one of them? Which means that 1 goes in cover 1 and the other 3 can be arranged in 3 factorial ways. So 3 factorial plus 4C2 times. Now 2 of them are true, which means 1 goes in 1 and 2 goes in 2. Right? So other 2 can be arranged in 2 factorial ways. Right? Minus 4C3 times. 3 conditions are true at a time, which means 1 goes in 1, 2 goes in 2 and 3 goes in 3. Now other 1 can be arranged in 1 factorial way. And plus 4C4 times. All the conditions are true, which means now we have to arrange 0 objects only. Which means 0 factorial is also 1. Only one way. So this is your answer, right? Okay. So I will try to expand it. Okay. I will try to expand it. That way it will be simpler. So we will try to pull out a few things. We want to get a closed compact notation. So I will try to get a compact notation for 4 first. Then we will do it for n. So what this will become 4 factorial minus, what is 4C1? N factorial upon n minus r factorial. 4 factorial upon 3 factorial 1 factorial times 3 factorial plus what is 4C2? I'm just expanding NCR. N minus r factorial times 2 factorial minus 4C3 is 4 factorial upon n minus r factorial times 1 factorial plus what is 4C4? 4 factorial upon n minus r factorial times 0 factorial. Right? So always this and this will cancel, this and this will cancel, this and this will cancel, this and this will cancel. 0 factorial is 1 only anyways. So what will this become? You can take 4 factorial out. If you take 4 factorial out, you will get 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. This is the expression, right? And this is the expression which is written here as well for n. I will solve it for n as well, but yeah, this is the expression. So 4 factorial times 1 minus 1, so this, okay? So yeah, you can calculate it as well. This will come out to be, so these two will cancel out, 1 minus 1. So this becomes 4 factorial upon 2, 24 upon 2 minus 24 upon 3 factorial, 3 factorial is 6 plus 24 upon 4 factorial, which is 24 only. So this will become 12 minus 4 plus 1, which is 9. Okay. So this is the fourth, this is subfactorial 4. By definition now this becomes subfactorial 4, which is 9. This expression entirely was subfactorial 4 only, right? We say that the fourth dearrangement number is subfactorial 4, which is 9. So we calculated subfactorial of 3 as 2 and subfactorial of 4 is 9. Okay, now how do we do it for n objects? Very simple, right? Again, use the inclusion-exclusion. Same way. Now we have n objects and n cover letters. So we will create n sets. 1 goes in 1, second is 2 goes in 2, and so on. Nth set is n goes in n. Nth letter goes in nth cover. So how many ways can we do this? Total number of ways is n factorial minus one of the condition is true, which means n conditions. nc 1 times one of the conditions is true. Let's say first is true. So 1 goes in cover 1. So the remaining n minus 1 can be arranged in n minus 1 factorial ways. Plus nc2 into, it will come out to be n minus 2 factorial, because two conditions are true, remaining n minus 2 can be arranged in these many ways. Plus minus so on. And the last term will be minus 1 to the power something ncn times 0 factorial, n minus n factorial, right? All the conditions are true. So minus 1 to the power will be what? See, for 1 it is negative. I always told you like how to calculate the minus 1 to the power. Just see the pattern. For 1 it is minus, for 2 it is plus. So for I basically it is minus 1 to the power I, right? So for n it will be minus 1 to the power n, right? So plus minus 1 to the power n, ncn 0 factorial. Now we have to expand it, n factorial minus nc1 is what? N factorial upon n minus 1 factorial 1 factorial times n minus 1 factorial plus nc2 is what? N factorial upon n minus 2 factorial 2 factorial n minus 2 factorial minus so on plus minus 1 to the power n. ncn is what? N factorial upon 0 factorial n factorial times 0 factorial. Now this cancels, this cancels, this cancels, and we can take n factorial out. This is like, we are calculating subfactorial n only here, right? So we can take n factorial out. This will become 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on, plus minus 1 to the power n by n factorial. Okay, so it's like alternate terms, 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on up to n. Okay, and this entire expression, okay, I will get there, but yeah, this is subfactorial of n, this is subfactorial of n, this is the nth subfactorial number. Cool. You have to calculate it sometimes, like it might be tedious. There is no very compact notation, there is a long notation only. So let's say you have to calculate the subfactorial of 10. You have to do 10 factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial up to 1 by 10 factorial. But there is an easy way to do that as well. I will tell you how. But yeah, this is the nth subfactorial number or the nth dearrangement number. Okay. This is the formula. Okay, this is the same formula, okay, just written in summation notation. The same formula but written in summation notation. So you can put I equal to 0, you will get this. I equal to 1, 2, 3. Okay, so this is the formula. Now, there is a quick observation. So what is the observation? Let's say I want to calculate subfactorial 10. It will be a like very tedious process, right? What is subfactorial 10? The number of dearrangements of 10 numbers. It will be 10 factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial and so on. Plus at the end we will have plus 1 by 10 factorial. Right? See, what happens is, calculating this will be very difficult, right? Very huge numbers. So it will be like, it will take a lot of time. But there is an easy way to do this. How? What we can do it, we can make it an infinite series. See, we have plus 1 by 10 factorial here. But it doesn't matter. We can actually have minus 1 by 11 factorial plus, if I add this, plus 1 by 12 factorial, minus 1 by 13 factorial, and so on up to infinity. Will it change it a lot? See, these terms, I have added this entire term. This term is very small. How? What is 1 by 11 factorial? Think about it. What is 1 by 11 factorial? It is a very, very small number, right? And think about it, like 11 factorial. 10 factorial is 3628800. This is 10 factorial. And 11 factorial is 11 times this. And you have 1 by 11 factorial. Right? It will be a very, very small number. And similarly, you subtract a very small number, you add a very small number, and so on. This entire term will be a very, very small number. It doesn't matter, right? It won't even matter. So generally what happens is, after 6th or 7th dearrangement number, the terms after that will be very small, almost negligible. You can actually add it. It won't change the answer very much. So what we can say it, if I add this, the subfactorial of 10, I can basically say that the subfactorial of 10 is approximately very closely equal to this entire thing. I have not stopped here. Ideally I should have stopped here, but I am not stopping here. I am adding this entire term as well. Okay. Why? Because this entire term is very small. It won't change the answer very much. But why am I adding this? See, I am adding this because this entire series is nothing but 1 by e. Okay, this is the expansion of 1 by e. E is 2.7 something, right? Like, so this entire expression is 1 by e only. So that way I can solve it much easier, right? I just have to calculate 10 factorial upon e. And I am very sure that subfactorial of 10, see, this won't be the exact answer. Ideally the answer will be an integer. This won't be an integer, right? E is an irrational number. How can this be this can never be a rational number. This will be an irrational number. Since like the numerator is rational and the denominator is irrational, right? This will be an irrational number, but it will be very closely equal to subfactorial of 10. See, we cannot do it for 3 subfactorial of 3. Because subfactorial of 3 will be factorial 3 times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. Right? I cannot add the other terms here. Because here the difference will be large. Because we are adding larger terms, 1 by 4 factorial. 1 by 4 factorial is very, very larger as compared to 1 by 10 factorial. Right? So here adding it will have a so you cannot say that subfactorial of 3 is approximately equal to 3 factorial upon e. It will be, but the difference will be large. But once you go to higher numbers, let's say you want to calculate the number of derangements of, basically after 5 or 6, this theorem will be okay. You can apply it. So if you have to calculate the 7th dearrangement number, you can just directly calculate 7 factorial upon e in your calculator. So you'll get a scientific calculator, directly you can calculate 7 factorial upon e, and the 7th dearrangement number will be very close to that number. Okay? Even you can open the scientific calculator and do this. So like if you want to do practice always, like in the exam you will get. So what you can do is, while doing practice, you can search for TCS scientific calculator. Okay, this is the calculator that you get in your exam, right? So if you want to calculate subfactorial of 7, this is the exact calculator that you will get in exam, right? So you just do 7, they have everything. You just do 7 factorial, there is factorial as well, yeah. 7 factorial upon e, there will be e as well, e. E is 2.71, okay. So you're getting 1854.112. Then definitely the subfactorial of 7 is 1854. Okay, it is very approximately equal to. Generally they won't ask you, like even if this question comes, they won't ask you, like the range of the numbers will be very like far away. So you can always select 1854. And actually like the subfactorial of 7 will be 1854. I can prove that. See, what is subfactorial of 7? It is 7 factorial times 7 factorial times 1 minus 1 factorial. We can cancel that term. 1 minus 1 factorial is 0. So now plus 1 by 2 factorial. So it will become 7 factorial upon 2 factorial minus 7 factorial upon 3 factorial plus 7 factorial upon 4 factorial, right? Plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial. So minus 7 factorial upon, so actually it is, it will take up all the space. I don't think you will be, yeah, it is there, okay. So plus factorial 7 upon 4 factorial minus 7 factorial upon 5 factorial plus 7 factorial upon 6 factorial. See, that way it is like a huge expression, right? Just to even write it. Plus this minus 7 factorial upon 7 factorial, which is minus 1 only. So I can do minus 1. 1854, okay? So the 7 factor, subfactorial 7 is 1854, which is like, that's what we get when we do 7 factorial upon e also. So that's an approximate value, okay? That's an approximate value of subfactorial of n. So for large n, I can write it for large n. Large means like above 7, above 6, 7. For large n, subfactorial of n is equal to n factorial upon e. That's all. That's what is mentioned here. If limit n tends to infinity, subfactorial upon n factorial becomes 1 by e. So what does it mean? What does it mean? What does this expression mean? It means that what we got? We got subfactorial of n is n factorial upon e, right? And 1 by e is approximately 0.367. 1 by e is approximately 0.367. It means that subfactorial of n for a large n is approximately equal to 0.367 times factorial n. This is the number of derangements. This is the number of arrangements. This is the number of derangements. This is the number of arrangements. It means that approximately 36.7% arrangements are derangements in general. This is a very small number, right? There are only 37% arrangements in which none of the objects are in the correct place. Think about it. In long term, let's say for 10 objects, there will be 3628800 permutations, right? Very huge. But approximately only 36% of them will be such that none of the objects are in the correct place. That's what this means, okay? So we can write this statement: approximately 36.8% arrangements are derangements for a bigger n, for n greater than 7, 8. Okay. Cool. So again, like very easy question, number of derangements of 1, 2, 3, 4. And this can be framed like this as well. Number of ways in which a teacher can give 4 students assignments if none of them gets to get their own assignment. Okay. Number of derangements of 4 is what? Subfactorial 4 is 4 factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. We already calculated it, right? It was 9. It is 6 actually. Okay, so we might have made a little mistake. The value will come out to be 6. So let me do it again. Okay, so that 1 minus 1 factorial gets cancelled. It becomes 24 by 2 minus 24 by 6 plus 24 by 24. So it becomes 12 minus 4 plus 1. It's 9 only, right? It's 9 only. Okay, so here it is a mistake. Cool? Cool. So in how many ways can we arrange 1, 2, 3, 4, 5, 6 in such a way that no even integer is in its original position? See, now here this is not standard dearrangement. Here it is not standard dearrangement. Here what they are saying is there are 6 places: 1, 2, 3, 4, 5 and 6. And we have to arrange these 6 objects 1, 2, 3, 4, 5, 6 such that only no even integer is in the correct position. So basically 2 should not go here, 4 should not go here, and 6 should not go here. Other we don't care about other numbers, but only even integers should not go in the correct places. So here this is not standard dearrangement. We have to apply inclusion exclusion only. So let's say the set S1 is 2 goes in the cover 2, S2 is 4 goes in the cover 4, and S3 is 6 goes in the cover 6. That way we have to solve it. So what is the total number of arrangements? It is 6 factorial minus, now 3 times any one of them is true, right? S1 minus S1 minus S2 minus S3, like all of them are symmetrical, so that's why 3 times. Let's say 2 goes in cover 2. So in how many ways can I arrange the remaining 5? 5 factorial. Plus, now two of the conditions are true, S1 and S2 both. So again S1, S2, S2, S3, S1, S3. So 3 times. Now 2 goes in 2 and 4 goes in 4. In how many ways can I arrange the remaining 4? 4 factorial. Minus, all the 3 conditions are true. If all the 3 conditions are true, the remaining 3 can be arranged in 3 factorial ways. So this is your answer, you can calculate it, okay? This will come out to be 426. Cool. So there are 426 ways. So now if such a question comes, you cannot apply the direct dearrangement formula because there is a specific demand. You have to apply the inclusion exclusion principle and solve it. Cool. So this is what dearrangements are. And this concludes all the basic elements of counting. Okay. So like whatever we have seen, inclusion exclusion, binomial, multinomial, theorem, cyclic arrangements, combination with repetition, very important, and dearrangement. There are a few advanced topics as well, like group polynomial and like there are a few advanced topics. They are like not exactly required for GATE syllabus, but later I will whenever we get time, I'll upload a few videos on that as well. If you have time, you can see them. But yeah, like for GATE syllabus, this is what we have discussed. This is enough, okay? And generally questions will come from here only. Cool. So now we will start in probability and statistics, counting is over. So we will start the elements of probability next. Cool. See you tomorrow. Bye.